Hello everyone, my name is Ben Mansur and I will be answering question 14.5 in which we will use freezing point depression to determine the molecular weight and formula for lysine. Question 14.5 reads, lysine, one of the amino acid building blocks found in proteins, contains 49.29% carbon, 9.65% hydrogen, 19.16% nitrogen, and 21.89% oxygen by elemental analysis. A solution prepared by dissolving 30 milligrams of lysine in 1.2 grams of the organic solvent biphenyl gives a freezing point depression of 1.37 degrees Celsius. What are the molecular weight and molecular formula of lysine? Here are our givens that are pertinent to answering the question. We are given the percent weight of each of the elements in lysine. We are given the mass of the solute lysine, as well as the mass of the solvent biphenyl in which lysine is dissolved. Note I have pre-converted the 30.0 milligrams of lysine to 0.030 grams, so this will not be shown in later steps. We are also given a cryoscopic constant of 8.00 degrees Celsius per molality. Also note that for the purposes of solving this problem, our units will be expressed differently as degrees Celsius kilogram per mole. This is achieved as we are multiplying degrees Celsius by the reciprocal of molality, as we are dividing by a fraction, as shown below. And finally, we're given a freezing point depression of 1.37 degrees Celsius. Our first step will be to find the empirical formula. In order to do this, we first divide the percent weight of the atoms by their respective atomic masses in order to get the relative number of atoms in each molecule of lysine. Doing this, we get 4.10, 9.57, 1.37, and 1.37 atoms for carbon, hydrogen, nitrogen, and oxygen, respectively. After finding the relative number of atoms for each of our elements, we then divide each of the relative number of atoms by the smallest calculated relative number of atoms in order to calculate the simplest ratio of atoms possible. Dividing each by our smallest relative number of atoms, 1.37, we end up with 3, 7, 1, and 1 for carbon, hydrogen, nitrogen, and oxygen, respectively. With this information, we can construct our empirical formula of C3H7NO. In step 2, we will find the molecular mass of our solute lysine in order that we can later use it to find our molecular formula. In order to find the molecular mass of our solute, we need to use our equation for freezing point depression, in which the molecular mass of our solute is hidden away in the molality portion of the equation. As listed in line 1, our equation for freezing point depression is our change in temperature, which is our freezing point depression, equal to the Van Hoff factor times cryoscopic constant Kf times molality. In line 2, we see the molality portion of this equation further broken down into its respective components. As we see, molality, defined as the value derived by calculating the moles of solute divided by the kilograms of solvent, can be further understood as the mass of our solute divided by the molar mass of our solute and the mass of our solvent multiplied together. If this orientation does not make sense, we can again look to line 1 and see that another way of wrapping your head around it is to think of the amount of moles solute, our numerator, as the mass of solute divided by its molar mass, times 1 over the mass of our solvent. It is important to note that this molar mass is reflective of our molecular formula, not our empirical one, which is why we are trying to solve for it. Moving on, in order to solve for the molar mass of the molecular lysine, we perform some simple algebra as shown in line 3, multiplying the entire equation by the molecular molar mass of lysine over 1, shown on the left, and 1 over the freezing point depression, shown on the right. This gives us the equation shown in line 4, in which we are now solving for the molecular molar mass of our solute lysine using information we already have. Moving on, we now plug our values into our reoriented freezing point depression equation, giving us our Van Hoff factor, which, as with most non-electrolytes dissolved in water, is 1, times our freezing point depression of 8.00 degrees Celsius kilogram per mole, times our 0.030 grams of solute lysine divided by our freezing point depression of 1.37 degrees Celsius times our 1.200 grams of solvent biphenyl. Calculating this expression and accounting for our significant figures of 3 and our units, we get 0.146 kilograms per mole, which we further multiply by 1,000 grams per kilogram to get a molecular molar mass of lysine of 146 grams per mole. Now that the hard part is over, we move on to step 3 and find the molar mass of our empirical formula. Remember from step 1, we discovered our empirical formula to be C3H7NO. Here in step 3, we multiply each atom in the empirical formula by its respective molar mass, which, accounting for significant figures, gives us a molar mass of 73.0938. Now with both our empirical and molecular molar masses, we can now divide them to find the constant in which to multiply our empirical formula to find our molecular formula. Doing this, we divide our molecular formula molar mass of 146 by our empirical formula molar mass of approximately 73 to give us a constant of 2. Note, it is not important to factor in the decimals after 73, as we are simply looking for a whole number constant, given that atoms of the elements in lysine do not exist in less than whole atom quantities. Multiplying our empirical formula by our constant of 2, we finally get our molecular formula for lysine of C6H14N2O2. Summarizing, in step 1 we construct the empirical formula by first finding the relative amounts of atoms from the given percents and then dividing the relative amounts by the smallest calculated relative amount to find the simplest ratio of atoms possible. In step 2, we find the molecular molar mass hidden away in the molality portion of the equation for freezing point depression. In step 3, we find the molar mass of the empirical formula by adding the molar masses of its elements. And finally, in step 4, we find our molecular formula by first dividing our molecular molar mass by our empirical molar mass, and then finally multiplying our empirical formula by the quotient of the molecular over the empirical molar mass. Thank you for watching, and I hope you learned something.